Everyone. In this video, we are doing diabetic prediction project using deep learning models. In here, we use MLP, CNN, LSTM, and TabTransformer model for predict diabetes. First, I start by downloading the dataset from Kaggle using the Kaggle Hub library. It's a CSV file with 100,000 rows on patient features like age, gender, BMI, blood glucose, and whether they have diabetes. The path gets printed so I know where it's landed. Next, I import my tools, pandas and numpy for data handling, seaborn and matplotlib for plots, plus some from skitlearn for preprocessing and smart for balancing classes, and joplib for saving models later. Then I load the data into pandas data frame with the function and peek at the first 5 rows with head function to see columns like gender, age, hypertension and target, diabetes, 0 or no, 1 for years. I check the shape 100 rows and 9 columns. Show the data types mostly float and integers with 2 objects for gender and smoking history and confirms no missing values. For deeper look, describe function gives that average age 42 looks balanced enough, but we'll handle imbalances later. Finally, I visualize categorical features for gender and smoking history. Lastly, there is a class imbalance in the dataset. Non-diabetic patients are more higher than diabetic patients, so that we use smart technique for balance the dataset. This is the class distribution after the smart. So then we split the train and test set. Then it save into the Google Drive.
We'll explain how we built a diabetes prediction model using a multilayer perceptron, a type of neural network. We started by mounting Google Drive to access files and storing necessary libraries. Next, we loaded a dataset containing health indicators such as age, BMI, blood glucose levels, and more. We explored the data, visualizing distribution, correlations, summary statistics, and pair plots. For preprocessing, we clean the data by managing missing values and outliers, since model work with numbers. Categorical data like gender was converted using encoding. We then scaled features to normalize them because diabetic causes were fewer. We applied smart to balance the classes, which helps the model learn both diabetics and non-diabetic patterns. We split the data into training and testing sets. The MLP model we built has input, hidden, and output layers. Hidden layers use ReLU activation to capture nonlinear patterns. The output layer uses sigmoid to predict diabetics probability. The model was compiled with the Adam optimizer and binary cross entropy loss, then trained over multiple epochs to minimize loss and improve accuracy. After training, we tested the model using metrics like accuracy, precision, recall, and F1 score to evaluate performance. Finally, a well-tuned MLP model can predict diabetes on new patients' data, aiding in early diagnosis and better health care. Thank you.
Build CNN model. Define the function build CNN model to create sequential 1D CNN. It used to convolutional block conv 1D batch normalization drop flow by global average pool in 1D and final dense layer with sigmoid activation for binary prediction. Compile model. Configure the model for training. Use the Adam optimizer and binary cross-trophy loss function. It track key classification metric accuracy, precision, recall, and AUC. Define callback. Set up training callback early stop, prevent overfitting, adjust learning and model checkpoint, best model weight based on validation AUC. Train model start the train process for up to 100 approach using the training data and validating on the test set with the defined callback. Evaluation model perform the final evaluation on the held out test data, returning the final loss and all compiled metrics. Mm, Classification report generate binary prediction and output the classification report, precision recall, F1 score, and the confusion metrics. Mm, Save. Finally, define the reusable function to take new data, load the best model and pre-processing tool, transform the data and output the final prediction probability.
Connected my Google Drive so I can use the dataset directly. Then I imported important tools like NumPy, Pandas, Matplotlib, and scikit-learn to handle and prepare the data. I also use TensorFlow and Keras to build and train the LSTM model. To get the same results every day, I set random seeds for NumPy and TensorFlow. Next, I open the train, CSV and test. CSV files from Google Drive using Pandas. The target column is datasets, which shows if a person has data set diabetes or not. I separated the dataset into two parts, X features and Y labels for training and testing. Then I use standard scaler to make all features have similar values, so no single feature is stronger than others. Because LSTM needs data in a sequence format, I reshape the data into 3D shape, samples, time steps, and features. Each feature is treated as a time step so the model can learn the relationship between different patient details. The model is a bidirectional LSTM with two layers. First layer 64 LSTM units plus dropout plus layer normalization to avoid overspeed. The second layer, another bidirectional LSTM with 32 units plus batch normalization. Then dense layer with ReLU activation. Finally, a sigmoid output layer that predicts the chance of diabetes. The model uses the Adam optimizer and binary cross entropy loss, and it checks performance with accuracy and AUC. I trained the model with early stopping and learning rate reduction to improve results and prevent overfitting. I watched the accuracy and AUC during training. The model gave high accuracy and AUC on test data. The graph showed steady improvement, and I saved the trained model to Google Drive for later use. In short, this code builds a strong deep learning model using its LSTM to predict libraries, showing how sequence learning works well even on medical data.
Hello everyone. Today I'm walking you through my diabetes prediction project using a TabTransformer model in PyTorch tabular. It's neural network that handles tabular data like patient record to predict diabetic risk, supervision for mixed categorical and numerical features. We start in Google Colab. For cell, I install key libraries with one pipe command, PyTorch tabular for the model, PyTorch Lightning for training, and Torch basics. It pulls everything in seconds. Next, I load my dataset. Think columns like age, BMI, glucose levels. I pre-process it, split into train and test, encode categoricals, normalize numerics, simple pandas magic, then it feeds into tabular model. Here's the core. I define the tab transformer, layers for attention on categories, embedding, and classifier head. Set hyperparameters like epochs, 50, batch size 512, optimizer Adam. One line kicks of training. It runs on GPU, spitting out progress like this: epoch 14, loss of 0.23 and 85% accuracy. After training, I evaluate the model, predict on test data, get matrices like accuracy and ROC, AOC, visuals pop up, confusion matrix, loss curves and loss curves. Then saved PNG for reports. Finally, save the model to drive tabular model ready for deployment.